Okay, so welcome to part 2 of lecture 10. Um, we have discussed that if you have a quantity that is an observable, A, and if we assume now this A can assume a finite set of values, and that there is just a single state that gives you uh, the corresponding value, we have seen that those states with a well-defined value of A form an orthonormal basis. Okay. Um, so we are discussing up to now the polarization of photons, and we have seen that the photon polarization is described by a column vector with two entries. So those are vectors that live in a vector space that has dimension 2. This means that in order to write the most general vector in this space, I need two vectors in the basis that I'll choose. Okay? So this means that if I compute, if I look at an observable that just depends on the polarization of the photons, I will have up to two possible values. And therefore, I will have two vectors forming a basis of, of, uh, of the space, of the vector space. And because of that, so if I give you a general polarization state U, the quantity A, namely the observable that you're going to measure, has not a fixed value. So as we saw in quantum mechanics, you don't have just a fixed outcome, but rather the probability of getting some possible values. Okay? This will be just true if the vector states that describe the photon coincides with the state Ej. And this state Ej, by definition, is the state which gives to me the value little a j for the observable big A. But in general, if I make a measurement for a general state U, I can have two different possible values for the observable A, and I'll call them A1 and A2. So if I measure A, I will either get A1 with some probability, or I will get A2 with other probability. Okay, that's how the system works. But I can compute those probabilities using postulate 2. Postulate 2 says to me, and now I'm just extending the postulate 2 because the way that I stated was a bit more restrictive. I'm saying that the probability of getting the value A1, I will call it P1, and this is obtained by the absolute value squared of the Dirac bracket between E1 and the state vector U. You see that why I chose E1, because E1 is the state that gives to me the value A1, okay? So if I want to compute the probability of getting the value A1, I take the state vector, so the state U, and I multiply it by the bra associated with the outcome A1, which is E1. Okay? In the same way that a photon, a photon in a polarization state theta had the probability of being found in the state of polarization phi by this expression. So I'm just mimicking this expression now for a different quantity A and not the polarization necessarily. The probability P1 of getting A1 is given by this expression, and the probability of getting A2 I will call as P2, and you obtain by taking the state U, multiplying by the bra E2, which is the state that gives to you A2. So if you are in the state E2 and measure the quantity A, you are going to get A2. And this is the probability, okay? I know that in the beginning this sounds weird, but you're going to get used to that. Don't worry, okay? So what is the interpretation of this is that assume that you prepare your system, okay? And this system is prepared in the state U. And now I want to measure the quantity A, okay, using this setup. So I will, and also let's assume that you can always repeat the experiment in the same conditions, okay? So you make the experiment, you make a measurement, you reset the experiment and make another measurement, you reset the experiment and make another measurement. I mean, uh, as much as you want, you are able to do this experiment infinitely many times, okay? So these probabilities, they mean the following. If you prepare the system in the state U and measure the quantity A, you are going to find the result of the outcome that you are going to measure will be A1 a number of times little n1. So you make the experiments several times, and n1 times you get the value A1, okay? And now you also can get another value A2, and you're going to see that n2 times, okay? So if you perform the experiment big N times, then for n1 times, you measure A1, and for n2 times, you measure A2. Of course, this since you can just get either A1 or A2, then N1 plus N2 must be the total number of times that you repeated the experiment. So now if you take the ratio between N1 and big N and the ratio N2 over big N, then if you increase the number of times that you repeat the experiment, if you increase big N, then these numbers will converge to the values P1 and P2, which are nothing but the probabilities, okay? This is the definition of a probability. So this is how you interpret these numbers that you get from these mathematical operations. This means that if you compute that, the likelihood of getting the outcome A1, if you perform the experiment n times, will be this number, okay, times the number of times that you repeated the experiment. Okay, so this is how you interpret the probabilities, and now I will define a quantity, but I will just define it, and we're going to elaborate about that next week. So I know that if I measure the observable A, I get two possible values, and those are A1 and A2, okay? But I can define a quantity which we call the expectation value of the observable A um, by the following expression. So you take, we define this as being this bracket here A. So this is, you read that as follows. This is the expectation value of A in the state U, okay? And this is nothing but this very simple way of taking, you know, a weighted average. You just sum over two possibilities, and you multiply the probability of getting A1 with A1, and sum with the probability of getting A2 with A2. So this is like the average that you do in exams. Okay? It's not a simple one because the probability of getting um, A1 and A2 might not be the same. Okay, so it might be that it's more likely to get A1 than A2. So the expectation value of A will be somewhat closer to A1. And then you define this quantity. But be careful, this quantity here, it gives you what we call the expectation value, which should not be confused with the value that you measure, okay? So if you make a measurement, you're not going to find the expectation value of A. You are going to find actually A1 or A2. So the expectation value is not the same as the values that you read out of your experiments, okay? But this has this is an important concept that will appear over and over. So that's why we introduce it. And for the moment, you can think of it as just being, you know, a formal definition. But well, what I do here is just to rewrite the expression in terms of those mathematical quantities, okay? So the expectation value of A in the state U is the sum of Pj times Aj. But Pj is the probability of getting the value Aj if the system is preparing the state U. And this is by definition just the absolute value squared of Ej times U. So I'm just replacing Pj by this expression here, okay? And this is Aj. Oh, sorry, and this multiplies Aj, which is here, okay? And now I can just rewrite this absolute value squared of this number as in the definition. So this is a complex number. So I just write the complex number itself times its complex conjugate. So the absolute value squared of a complex number is the number times its complex conjugate, and this multiplies Aj. Aj is here. And now I can just make an algebraic manipulation, which is if I flip the order of this product, so if I take the bra U and the cat Ej, since this is a complex number, I have to take the complex conjugate. Remember, for scalar numbers, sorry, for real numbers, if I replace the order of the vectors in the scalar product, I don't change the scalar product. But for complex numbers, if I exchange the order of the vectors, then I get the complex conjugate. So if I exchange the order here, this will give you Ej, sorry, this will give you U Ej. So this number is this number. And I just repeat this complex number here. times aj that I put here. So from this line to this line, I just did some algebraic manipulations and write the expectation value of A as being this expression here, okay? I will stop here because next time we're going to elaborate a bit on this expression, and I don't want to rush on that. And since you have the quiz now, I will stop because you have 30 minutes more of lecture in our time slot. And I want you to take that to organize yourselves and, you know, have at least 20 minutes to do the quiz. So I will stop recording. So thank you for your attention. I will stop now the recording.